Hi everyone, here's Ray from UC Santa Barbara. I'm going to introduce our work on text-guided 3D human generation from 2D collections. This project is also collaborated with Meta AI. 3D human has huge application values, such as gaming characters, virtual reality, or animation movie. However, it takes series of complicated operations to create a 3D instance, and this is very difficult for novice to get started. So if we have a system that can follow textual descriptions to generate the 3D human as we want, it can significantly improve the controllability as well as the accessibility. So in this project, we want to do text-guided 3D humans that can generate a 3D humans that present the assigned fashion patterns in the language. We present the compositional cross-model human, aka CCH, which is heavily inspired by EVA 3D. For a 2D image, we first adopt an external estimator to predict the SMPL parameters, like the shape and the pose, and its segmentation map. Then we do the inverse linear blend scaling to transform from SMPL coordinate into the canonical space, so that it can support the further nerve rendering. And we follow EVA 3D to divide a human body into 16 parts, where each part can perform individual volume rendering as a more efficient 3D generation. To achieve text-guided generation, we first extract the text features through the text encoder and fuse with the nerve features by the cross-model attention, and these steps can help directly inject the fashion features into each volume features. And then we can compose all body volumes together and jointly render our target 3D humans. To learn this framework, we have a semantics discriminator that considers all render quality, language alignment, and the matching to the segmentation maps. So the adversarial learning can help to ensure not only the concrete body, but also the semantic alignments, that our generated humans can present the exact fashion patterns in the language descriptions. For experiments, we use two datasets, Deep Fashion and SHHQ. Both of them contain pairs of 2D image and its fashion descriptions. For evaluation metrics, we'll calculate the FID score between the real image and our 3D generations. We'd also calculate the distance of the estimated steps map. And we can also calculate the correctness of key points to have a fine-grained quality evaluations. And to compare the alignment to the input descriptions, we consider the clip score and also the fashion accuracy between the generated human and the label of the fashion topics. For baseline, we have latent nerve and texture that relied on an external diffusion model to provide visual guidance to fine-tune the nerve model and the mesh texture. We'd also have the clip optimizations to leverage the clip alignment to iteratively optimize the nerve model. And all of them require the iterative optimizations, and in contrast, our CCH can obtain the result by just going through one step of the model. From the quantitative results, we can find that the clip optimizations is using a pre-trained EVA 3D, so it can have a good 3D quality. But because the alignment from the clip is not explicit enough, so the alignment to the fashion descriptions is not good. Even texture can perform better than them. And because our CCH is using the compositional human with the cross-model attention, we can fuse the fashion features directly into the nerve features, so that we can have better 3D quality as well as the fashion alignment to the language descriptions. So we can see that we can present the graphic pattern tank top as well as the short sleeve striped t-shirts. And it is obviously that the clip optimization cannot present the correct long denim pants. Similar result can be found in the human evaluation. Both Clip O and our CCH can have high quality of the 3D humans, but only our CCH can outperform all baselines and achieve the best relevance to the language descriptions. And because we only have to go through the model for one time, our CCH are extremely faster than all baselines. So we can have the lower time cost and also the least GPU consumptions. And with the external motion model, we can also control the motions using the language and make the generated 3D human animated, such as kicking soccer or shooting basketball. Cool. So the takeaway is we introduced the text-guided 3D human generation, which leverages the compositional human as well as the cross-model attention to inject the fashion information into the nerve features. And the fusions with nerve rendering can enable the high quality and also the high efficiency. And our model can also support for 3D human editing, such as changes the colors of the tank top or the black pants. We can also make the long sleeve into a sleeveless. So that is all about our project. Here's Ray from UC Santa Barbara. Thanks for all your listening.